everyone. So today I will be presenting about volumetric analysis, specifically the determination of the concentration of acetic acid in vinegar through acid-base titration. Volumetric analysis is a quantitative analytical method used to determine the concentration of an unknown solution by measuring the volume of a standard solution required for a complete reaction. This technique commonly involves a titration process where a solution of known concentration called the titrant reacts with a solution of unknown concentration known as the analyte. The endpoint of the reaction is usually identified by a color change with the help of an indicator. In this experiment, phenolphthalein is used as an indicator. It changes from colorless to a faint pink color when the endpoint is reached. The experiment involves titrating vinegar, which contains acetic acid, with a standardized sodium hydroxide or NURHUSNA solution. Since acetic acid is a weak acid and sodium hydroxide is a strong base, they undergo a neutralization reaction. By measuring the volume of sodium hydroxide required to reach the endpoint, we can accurately calculate the concentration of acetic acid present in the vinegar sample. Next, the objective of this experiment are divided into three main parts. First, to apply volumetric analysis techniques in determining the concentration of acetic acid in vinegar. Second, to perform an acid-base titration using a standardized sodium hydroxide solution. This allows us to observe the neutralization process and accurately identify the endpoint of the reactions. Third, to calculate the concentration of the unknown acetic acid solution based on the titration data obtained. Accurate volume measurement and proper titration techniques are essential to ensure reliable and precise results. Through this experiment, we gain practical experience in titration methods and develop a better understanding of quantitative chemical analysis.
Today, I will be discussing the theory of volumetric analysis, specifically focusing on how we apply this principle in our CHM256 laboratory work to standardize solutions and analyze real-world samples like vinegar. Let's dive into the core theory first. So, what exactly is a volumetric analysis? At its core, it's a quantitative technique. That means we are trying to find an exact amount or concentration. We do this by taking an analyte, a solution where we don't know the concentration, and reacting it with a titrant which has a known concentration. The magic happens by measuring the exact volume of titrant needed to completely react with the analyte. For this to work perfectly in a lab, the chemical reaction must be incredibly fast. It must go to completion, and we have to know its exact balance of chemical equation. To understand volumetric analysis, we need to master four critical terms. The first one is the titrant is what we put in the burette. It's our known standard. And next is the analyte is down in the conical flask, which is like our mystery solution. Now, that is a very important theoretical distinction we need to make between the next two terms. The third one is the equivalence point. It is the exact moment in time when the moles of titrant match the moles of analyte based on the chemical equation. It is purely theoretical because we can't see molecules. We use an indicator to give us a physical change, usually a color change. The moment that the color changes permanently is the final pillar, which is the end point. In a perfect world, these 2 points will be identical, but the tiny gap between them is what we call our titration error. Not all chemical reagents are created equal, which brings us to the primary versus secondary standards. A primary standard is the gold standard of the lab. It is highly pure, chemically stable, doesn't absorb moisture from the air, and has a high molecular weight to minimize weighting errors. In our lab, for example, we use sodium carbonate, which is the Na2CO3, as our primary standard. On the flip side, we have secondary standards such as the hydrochloric acid, HCl, or sodium hydroxide, NaOH. Their concentrations cannot be trusted just by weighing them out. For example, NaOH pellets are highly hygroscopic, meaning they aggressively absorb water and carbon dioxide from the air the moment you expose them. Because their mass is constantly changing, we must standardize them against a primary standard to find the true concentration. Okay, moving on to the standardization of HCl, we apply this in part A of our experiment. For example, since HCl gas can evaporate from solution, its concentration drifts. To find its exact molarity, we titrated it against our stable primary standard sodium carbonate. Like, for example, the stoichiometry shows a 1:2 ratio. This means for every 1 mole of sodium carbonate in our flask, it takes 2 moles of hydrochloric acid from the burette to neutralize it. By tracking the exact volume of HCl used to reach the endpoint, we can use the mole ratio to calculate the highly accurate molarity of our HCl. Let's move on to the vinegar analysis. Alright. So once we have standardized our solution, like the ratio 1:2 mole, we can use them for practical applications, like analyzing commercial vinegar in part B. Vinegar contains acetic acid, and we want to find its percentage weight by volume. We titrate the acetic acid with our standardized sodium hydroxide. This is like a clean 1:1 ratio of molar reaction. However, Commercial vinegar is far too concentrated to titrate directly. It will require way too much titrant and waste material. So a crucial step in here is dilution. We dilute the vinegar first, perform the titration, and calculate the molarity of the diluted sample, and then multiply by our dilution factor to find the original concentration. Finally, we convert that molarity into grams per 100 ml to get our final percentage. To wrap things up, volumetric analysis is like an elegant and highly accurate method, but its success relies entirely on laboratory precision. Understanding the difference between primary and secondary standards ensures our baseline is correct, and distinguishing the theoretical equivalence point from the experimental endpoints help us understand our limitations and error.
Moving on to procedure, the determinations of acetic acid in vinegar. First, a 10 ml aliquot of vinegar was transferred into a 100 ml volumetric flask using a pipette. The solution was diluted to the calibration mark with distilled water and mixed roughly. Second, a burette was rinsed with distilled water followed by small amount of standardized NaOH solution. The burette was then filled with the NaOH solution and the initial reading was recorded. Third, a 20 ml aliquot of the dilute vinegar solution was pipetted into a 250 ml conical flask. Fourth, 2 to 3 drops of phenolphthalein indicator were added to the conical flask. 5. The dilute vinegar solution was titrated with NaOH from the burette while continuously swirling the flask. 6. As the endpoint was approached, NaOH was added dropwise until a faint pink color persisted for approximately 30 seconds. 7. The final burette reading was recorded. 8. The volume of NaOH used was calculated by subtracting the initial burette reading from the final burette reading.
Now, I would like to present the results of our experiment. In this experiment, 20.00 milliliters of diluted vinegars was titrated with a standard sodium hydroxide solution with a concentrations of 0.1000 molar. The titration was repeated 3 times to improve the accuracy and reliability of the results. The volume of sodium hydroxide used were 15.7 milliliters, 15.0 milliliters, and 14.8 milliliters. The average volume of sodium hydroxide required to reach the endpoint was 15.17 milliliters. The reaction that occurred was a neutralization reaction between acetic acid and sodium hydroxide, producing sodium acetate and water. Since acetic acid and sodium hydroxide react to a 1:1 mole ratio, the average volume of sodium hydroxide can be used to calculate the concentrations of acetic acid in the vinegar sample. Next, I will explain how the concentrations of acetic acid was calculated. First, we refer to the balanced chemical equation, which shows that 1 molar of acetic acid react with 1 molar of sodium hydroxide. Then, we applied the titration equation to determine the unknown concentrations of acetic acid. The known values used in the calculation were the concentrations of sodium hydroxide, which was 0.1000 molar, the volume of the vinegar sample, which was 20.00 milliliters, and the average volume of sodium hydroxide used, which was 15.17 milliliters. After substituting these values into the equations, the concentrations of acetic acid in the diluted vinegar sample was calculated to be 0.0759 molar. This result represents the concentrations of acetic acid in the diluted vinegar based on the average titration values obtained.
In conclusion, this presentation has explained the principles and applications of volumetric analysis as a quantitative method for determining the concentration of an unknown solution. We have also described the acid-base titration process using standardized sodium hydroxide as the titrant and vinegar containing acetic acid as the analyte, as well as the role of phenolphthalein in identifying the endpoint through a light pink color change. This presentation has also demonstrated how the volume of sodium hydroxide required at the endpoint can also be used to accurately calculate the concentration of acetic acid. Overall, volumetric analysis is a reliable and widely used analytical technique that depends on accurate titration procedures and precise endpoint detection. Its applications extend to quality control, food analysis, pharmaceutical testing, environmental monitoring, and many other areas of analytical chemistry, making it an essential technique for both scientific research and industrial practice. To improve the accuracy and reliability of volumetric analysis, several good laboratory practices should always be followed. First, performing multiple titration trials should help produce a more consistent average value and minimize random errors. Second, all glassware, including the burette and pipette, should always be properly rinsed with the appropriate solutions before use to prevent contamination. Third, the sodium hydroxide solution should always be added slowly as the endpoint approaches to avoid overshooting the color change. Fourth, the burette reading should always be taken at eye level to minimize parallax errors and ensure accurate volume measurements. And finally, using a freshly prepared and properly standardized sodium hydroxide solution helps maintaining the accuracy of the titration and the calculated concentration of the analyte. And that's all for this presentation.